So this problem is going to look at, imagine this is a sled, and we have a kid and the sled together are 49 kilograms, and they're being pulled along the snow by two additional friends. One friend is pulling at 10 newtons at an angle of 45 degrees, and the other friend is pulling at 8 newtons at an angle of 30 degrees. Now there is friction, so we know that there is friction acting on the sled, but we don't know the direction of the frictional force other than it opposes the motion of the sled. So we know that friction opposes the motion, and so its direction will be opposite the motion. So it's going to be somewhere, if the sled is moving off in the right-ish world, it's going to be somewhere in the left-ish world. But what angle that's acting on, we don't exactly know. So direction opposite the acceleration of the sled. So the sled is going to start from rest. The problem specifically reads that two children pull a third child on a snow saucer, exerting forces F1 and F2 as I've drawn here in this picture and described. What's the acceleration of this 49 kilogram sled and child system? And the direction of that frictional force is unspecified. So, but we know it will be opposite forces 1 and 2. So we want to know what is the acceleration of this sled. Okay, so how are we gonna figure that out? Well, first we have to examine that object, define the object, and define the forces acting on it. So let's just go through that process because it's really good for us to kind of keep that process in mind. Our object, of course, is the sled-kid combo. So we're interested in the forces acting on that sled. And what are those forces? Well, we have force 1, which is between the sled and friend 1. We have force 2 between the sled and friend 2. We have the frictional force, which is going to be between the sled and the ground. We know gravity's acting, so we have the force of gravity between the sled and the earth. And it's sitting on that sled, so we have a normal force between the sled and the ground. Now, if we look at a top-down view, which is what we're looking at here, we're going to really be looking at the acceleration along the plane of the ground. And so if we kind of looked at a side view, that force of gravity and that normal force, there's no acceleration in that direction in the plane, in and out of the board, or if we turned it sideways, above the ground, below the ground, that typically earth vertical direction. And so while these forces certainly act, they're not going to come into play. So we're not going to worry about that. They have no contribution to the problem we are actually interested in solving. And so we're going to only look at 2 dimensions in the plane of the motion itself. All right? Okay. So we first want to decide what we're interested in, the direction of the acceleration. We're interested in the magnitude of the acceleration. So we need to understand what is going to be that direction of acceleration. Now we know that friction always opposes the direction of motion. And so the direction of the actual motion is going to be dictated by the forces acting on this sled by the friends, these 2 pulls. So we're going to explore this problem in a little different manner in kind of parts and pieces, kind of conceptualizing it. And so these 2 forces are going to total the force of the motion of that sled, and that friction is going to oppose that motion. But we first need to find out the direction of the forces, the direction of friction, so we can then examine the total acceleration along that direction. So we're going to get to a space where we have one net force as the resultant of these 2 forces in one direction, friction in the opposite direction. So let's find out the direction of the frictional force by looking at the resultant of these two forces. So the net, I'm going to look at first the net force by the friends. That's what we're going to find out first. So how do we find that? Well, these are two force vectors acting on that sled. And so we're going to do a vector analysis of those two forces, trying to find the net force of the friends. So I'm going to redraw the two vectors. We have vector 1 at 10 newtons, and this is at 45 degrees. And I also have vector 2 at 8 newtons at 30 degrees. So how do I determine the resultant? Well, I have to break my vectors up into horizontal and vertical components. Horizontally, well, vector 1 is up and to the right, so there is a horizontal component, 10 times the cosine of 45, and there's an up component, 10 times the sine of 45. Similarly, the second force, force number 2, is 8. There's a right and down times the cosine of negative 30. Remember, I like to always reference to the positive x-axis. We're going in the the clockwise direction, and so it's negative 30, and the vertical component is 8 times the sine of negative 30. So if we get the resultant vector, I get both the horizontal and vertical components of that vector. We're going to get out our handy dandy calculator here. We have, I need to make that a little bit brighter. Excuse me. We have 10 times the cosine of 45 plus 8 times the cosine of 30. So I'm at negative 30, negative 30. Turns out the cosine of negative 30 and the cosine of 30 are the same number. That gives us a horizontal component of 13.999. We'll give it out a little bit, then we'll reduce at the end. The horizontal component for that net force by the friends of 13.999, so 14. And vertically, we have 10 times the sine of 45 plus 8 times the sine of negative 30. That 30 is going to be important because the sine of negative 30 is in fact negative. And it gives us a vertical component of 3.071. So I have my horizontal and vertical component. The force of the friends in magnitude is the square root of 13.999 quantity squared plus 3.071 quantity squared. So I'm going to use my Pythagorean theorem here. So we have the square root of 13.999 squared plus 3.071 squared. And that gives us 14.33 newtons is the magnitude of that net force, and the direction of that net force is going to be the inverse tangent of my vertical component, 3.071, over my horizontal component, 13.999. And if I take the inverse tangent of 3.071 divided by 13.99, I get 12.4 degrees is the angle that sled is going. So I have a force that the friends are exerting of 14.33 newtons and an angle of 12.4 degrees. Okay. So we are interested in the acceleration. It does tell us that the frictional force, it does give us the magnitude. I was like, we need the frictional force, or we have to find the normal force, which we are not equipped to do without the coefficient, as you all know by your studies of friction. But it does give us the frictional force. So I apologize, I didn't write this down. It gives us the frictional force on the sled which is equal to 7.5 newtons. We just did not know the direction. All right, so we do have the magnitude. Thank goodness we wouldn't be able to solve it. So now we know that the sled has a net force by the friends at an angle of 12.4 degrees. And the frictional force is opposite that direction. So we can now look at a problem, second half. We're going to take the second half of this problem and we're going to say, okay, let's imagine that my one dimension is along this line of 12.4 degrees. If it were along this line of 12.4 degrees, let's say it's along, that's about 12.4 degrees, then I have a net force on the sled. So this is going to be our free body diagram of the sled. I have the net force of 14.33 newtons by the friends collectively. And I have a frictional force in the same direction of 7.5 newtons. And so we need to determine the magnitude of the acceleration. Well, now I'm along one dimension, so these forces are in the same dimension. The net force acting on this sled along this 12.4 degrees is equal to the force of the friends minus the frictional force acting on the sled. The force of the friends combined is 14.33 newtons. Well, let's get rid of our little n there. I don't like putting units in my math equation. It gets too complicated. Minus the 7.5 newtons, and we get a total force of 14.33 minus 7.05. We get a net force of 7.28 newtons at 12.4 degrees. But remember, we want the acceleration. So our net force is equal to the mass times the acceleration. So our force divided by the mass is going to give us that acceleration. The force is 7.28 divided by my mass of 49 kilograms. I get an acceleration magnitude equal to 0.15 meters per second squared at 12.4 degrees. So I'm just going to bring that angle down. All right. So this problem we approached a little bit differently. We had to really visualize what was happening in this situation. We had to recognize that I have a frictional force, but I don't know what direction it's at. But I do know it opposes the motion. This motion is only going to be caused by the two forces acting along the plane. We recognize that our force of gravity exists, our normal force exists, not really relevant to our problem. So I first have to recognize that it's the net force due to these two external forces that's going to provide me the information about the angle at which the motion of the sled is going to happen. So I can find that net force by the friends and its angle. And then I can visualize this as two opposing forces. One pulling, friction, pulling in the opposite direction. Look along that line as a single dimension Newton's second law problem. Getting that net force, which allows me to get the acceleration at the angle that the object is moving. All right, good job.